Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on December 24, 2025, about a week ago. This paper introduces UltraShape 1.0, a two-stage 3D diffusion system that pairs aggressive watertight data cleanup with voxel-anchored refinement, so it can generate sharper, cleaner geometry even when trained only on public datasets. The paper is titled UltraShape 1.0, High-Fidelity 3D Shape Generation via Scalable Geometric Refinement. Alright, as we go, the voxel-based refinement idea turns out to be the key that makes high-detail generation scale. Also, the author shared a GitHub repo for UltraShape 1.0, and it is pretty practical. You will find the full inference pipeline plus pre-trained weights instructions, a main entry point, configs and scripts for sampling and multi-node training, and guidance for refining a coarse mesh generated by Hunyuan 3D 2.1. On Hugging Face, UltraShape 1.0 includes the refined model weights and a model card explaining the two-stage course to refine 3D diffusion pipeline, plus example guidance for running image to 3D generation. Figure 1 conveys the main promise, which is that the system can generate 3D assets with crisp, printable-looking geometry, rather than blobby surfaces. The full canvas shows a wide variety of shapes, so the point is generality across characters, vehicles, and buildings. The central cluster highlights complex structures like robots and towers, because those stress thin parts and sharp edges. The bottom row with the UltraShape text hints at fine detail that holds up when you zoom in, which is where refinement matters most. Figure 2 explains how the system turns an input image into a refined, high-fidelity 3D mesh. The full diagram lays out a two-stage diffusion transformer pipeline, where stage 1 makes a coarse mesh, and stage 2 adds detail using voxel-anchored refinement, meaning the model refines geometry at fixed 3D locations. The lower left panel clarifies how the variational autoencoder supports both surface queries and near-surface voxel queries, so marching cubes can extract the final surface cleanly. Figure 5 makes the data cleanup point concrete, because it shows how different water tightening methods change the actual mesh quality. This figure compares raw meshes to Dora, flood fill, visibility check, manifold plus, and the author's method at 2 resolutions. The visibility-based results tend to seal holes but add messy, blobby interiors, especially in thin parts. The 2 author columns stay clean and complete, and the 2048 version preserves sharper edges. Figure 6 shows that the two-stage refinement pipeline translates into visibly sharper 3D meshes than other open-source baselines. The full grid compares multiple objects across methods, with the input image on the left and several reconstructed meshes to the right. The UltraShape 1.0 column tends to keep thin parts and engraved details intact, which matters because these regions usually collapse into blobs. The Knight and Pagoda rows make that difference especially clear. The edges stay crisp. So, 2 takeaways stand out. UltraShape 1.0 treats data quality as a first-class problem with robust watertight processing, and it gets scalable detail by anchoring refinement to fixed voxels so the model can focus on local geometry. The broader implication is that open, curated pipelines can close a lot of the gap to expensive 3D generators. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.